Hello everybody, today I'm going to show you how to calculate pi using the inverse cosine function and again using the Maclaurin series method. So we know that the inverse function of inverse cosine x, and the derivative of inverse cosine x is equal to minus 1 over the square root 1 minus x squared. We can rewrite this fraction as this one, right? Minus parenthesis 1 plus parenthesis minus x squared together to the power of minus 1 over 2. And we know from the fundamental theorem of calculus that theorem linked the processes of differentiation and integration as the reverse process of one another. So what it means is that when you have a function that is continuous and differentiable, its derivative, the antiderivative of its derivative is the self. So from there you can say that the antiderivative of minus 1 plus minus x squared to the minus power of the minus 1/2 dx equal to the inverse cosine x plus c plus a constant c. So what does this tells us? Well, since we use the method, the Taylor series method, to calculate the value of pi, we can somehow link that method to this equality right here. So how do we do this? Well, there's in general there's a sort of like the expansion, you know, from pre-calculus or from algebra, you know that the law of polynomial expansion. So when you have a function, a polynomial function 1 plus x to some power k, okay, some power k, and you can, then this k is different from 1, 2, 3, 4, meaning all not k is not belong to the natural number. Okay, so when you have this, you can expand this as follows. You can say this equal to n start from sigma, n start from 0 to infinity, the index k and the index n, x to the n. What does this even mean? It means that we can rewrite it in some form. It's sort of like a normalization. We can represent this in terms of a series, or in and of itself, it's just the expansion, right? The polynomial expansion. So this will equal to 1 plus factorial, sigma notation, and start from 1 to infinity, and k times k minus 1 dot 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 k minus 1 plus 1 over n factorial times x to the n. Okay, so that is the sort of like the serial identity for 1 plus x to some power k, and k is not belong to the natural number. Okay, so of course it's not equal to 0, because anything with the 0 power is equal to 1, so that's not kind of defeat the expansion process. So when we have this, we can go ahead and apply to this one. This in another itself is just in this form where we normalize it already, and you know, here is minus 1/2. Minus 1/2 is not belong to n star. Right. So from this expansion, we can go ahead and apply for this one. We know that here we use whatever the x here in front of the behind the plus side. So behind the plus side, we have minus x to the x squared. So we go ahead and put in here, instead of x to the n power, we have minus x squared to the n power, right? And k here is minus 1/2, so here k will be minus 1/2. So we can go ahead and say, well, minus, we just take this whole thing, minus 1 plus minus x squared to the minus 1/2, okay? That is equal to, sorry, to the minus 1/2, okay? That is equal to the, we can go ahead and say this one, okay? We can go ahead and say n equal to 0, k is minus 1/2, and n, and x is here is minus x squared, so we can go ahead and say minus x squared to the n. Okay. Alright, so we can go ahead and expand this following this expansion. So what do we have here? This equal to 1. Well, since we have a minus sign here in front, so we need to be careful about the sign as well. So we have a minus here, okay? That's the minus, right? It's a minus in front. So minus parentheses 1 plus, what is this? This is factorial, sigma notation, and go from 1 to infinity. K is minus 1/2, so we say minus 1/2, right? Minus 1/2 minus 1 times dot 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 k minus 1/2 minus n plus 1 over, what is this equal to? Is it over n factorial x to the n, okay? Minus x squared to the n. Alright, so how do we from this expansion, how do we write out the series? What does this even mean, right? So let's just write out what it means, and we can start from there. We start at n equal to 1. So what does it mean? Well, we have the n term here, the normalization, or the sort of like a format of how this this sort of product would work at the n term, right? We format the n term. So the n term we format to be minus 1 over 2 minus n plus 1. N start at 1. Okay, so we start at n start at 1. Put n equal to 1 in. Minus 1/2 minus 1 plus 1. That is just minus 1/2, right? So n equal to 1. 1 factorial, that's 1. And here's 1, so that's just minus x squared. Just minus x squared, so we have, so we go ahead and write that minus 1/2, alright, over 1 factorial minus x squared, because n is 1, so we just leave it that way. Okay, so what is the next term that we have? We have n start at 2. Okay, so how do we do this? N start at 2. N minus 1/2 minus 2 plus 1. That's minus 1/2 minus 1. So it's coincide with this one, right? So is what does it mean to have something like this when we format this way? It means that we times up until that n term, right? Whatever the front, we keep it, and we times the n term, whatever the n term is, we time up until that term. So here we have is minus 1 already. So we times up until that n term, n is 2, and minus 1 over half minus 2 plus 1, that minus 1/2 minus 1. So this term, right? So we time up into this term, right? Up into this term, so we have minus 1/2 time minus 1/2 minus 1 over, because n start at 2, so this is 2, n is 2, so this is 2 factorial. This is minus x squared to the second power. That's the positive, right? So we have x to the 4th. Okay, so next what do we have? Alright, so n n is 3, right? So minus 1/2 minus 3 plus 1, so that's minus 1/2 minus 2. So we times up into that term, minus 1/2 minus 2. So we times up there. What would we have before we keep it, right? We keep the whole product. So in front, what do we have? Minus 1/2, alright? Minus 1/2 minus 1. Times up into that term, right? Minus 1/2 minus 2, right? Because 3 put in here, that's minus 3 plus 1, that's minus 2. Alright? So we times up into that 3 factorial. Okay? X to the n is 3, so minus x to the 6th, right? So minus x to the 6th. Okay? Plus dot dot dot. Alright? So now we go ahead and simplify it and see what we have. So we can write something like this: 1 plus a minus and minus, that's plus, right? So x squared over 2. We can sort of see here that every time we times up and we add up a power, we add up another term in this product up in the numerator. So it means that the negative sign will cancel each other. So we will end up having a positive sign for every term. So we can have the plus sign for every term, right? So we have x squared over 2, right? Minus 1/2. This is minus 1/2 minus 1. That's minus 3 over 2. So we can write 1 times 3. 2 down in the denominator. That's 2 times 2, so we can write it as 2 squared, right? 2 squared times 2 factorial. With series, every time there's a repetition like this, when there's 2 times 2, 2 times 2 times 2, things like that, we should kind of put it in its power, in its polynomial form. Right here we have 2 to the 2nd, 2 to the 2 squared. Here you can say 2 to the 1, and here later on we can have 2 to the cube, right? 2 cubed. We put that so that it'd be easier for us to format or to formalize the pattern. So here we have 1 times 3 over 2 squared times 2 factorial, x to the 4th, right? Okay, plus. Now here's minus 1, here's minus 3, right? Minus 1 over minus 2, that's minus 5 over 2, right? So we can write this minus, minus, minus. We say that's this plus side all around, so it's a plus, right? So we can write 1 times 3 times 5, 2 cubed times 3 factorial, x to the 6th. Right? Okay. The minus sign is always coupled together to give us an even power. That's why it's always plus. So we have plus dot dot dot. Okay. All right. So what do we do next? Well, previously we talked about this using the fundamental theorem of calculus. What do we say? We say that the antiderivative of the derivative of inverse cosine, which is minus x plus minus x squared minus 1/2 dx, is equal to the inverse cosine of x plus c, right? So this derivative we say is equal to this series. We already expanded it. Antiderivative is equal to that. Okay, so let's try apply antiderivative for this whole series and see what we have. So therefore, this term would equal to antiderivative of 1 plus x squared over 2 plus 1 times 3, 2 squared times 2 factorial, x to the 4th plus dot dot dot, right? We can write out many terms as we want together d of x, right? Okay. Alright, so you can write something like that and then apply antiderivative for that. What do we have? We can have x, right? this is power, second power, times it up by another, so that's a cube. You gotta divide by the constant that you already times up, which is 2, so 2 times 2 is right, 2 times 2. Right. For this one, keep the same constant. Okay, x to the 5th, right? Over 5, so we can write 5 here. Okay, alright. We can do one more term, which is 1 times 3 times 5 here. Right, 2 here, times 3 factorial times 7, x to the 7. Okay. Plus c. Right? Because there's no endpoints. That's why we're going to add a constant c. Right. So we have this, and this whole thing, right? This whole series we expanded. We said it before, right? Previously we said this to equal to inverse cosine x plus c. Okay. So we can put the c together and put the c on one side. So it's the same thing, it's equivalent as writing this. Alright? It's equivalent as writing this equal to this whole thing. So we have this expansion, very great. So how do we do next? What are we going to do? Well, we calculate pi, right? So same thing as the previous video I have shown you. It's the same thing as finding the appropriate ratio value and plug in here to get out a radian value, or to get out an angle value or an angular value. So how do you find appropriate value for x so that you can find the value of pi? So how do we do that? Well, first, before we do anything, we have this constant c here. We have something that is undetermined, right? So that's something that's quite not specific, so we've got to take care of this c. What is that c equal to? One thing, we can apply the initial value into this function right here and find out what's c going to be equal when we plug in a value that in the domain of inverse cosine of x. Well, we know from trigonometry that the inverse cosine of x has a domain d, right? That d between -1 and 1. Okay? Alright. So this includes 0. Maybe you can probably write out the range as well. So the range is from 0 and pi. So this domain includes 0. So what it means is that the inverse cosine of x is continuous, differentiable at 0, because we have a convergence series when we evaluate its derivative, right? So it means that we can plug in the value 0 here. So we plug in x equal to 0, what happened? So let's see. So when x equal to 0, so when x is equal to 0, we have inverse cosine at 0 equal to, here we have the term x throughout for every term, for every term to infinity, except the c. We don't have anything for the c, so that equals to c, right? But we know from trigonometry that what is the inverse cosine at 0? Well, we know that cosine pi over 2, which is cosine at 90 degrees, equal to 0.